Warning: I am by no means an expert. In an ever changing field which demands constant learning, growth, and adaptation, I'm not even sure what the term expert really means. I'm just a nerd who loves to nerd, so let's do some nerding. I love computers, always have, and probably always will. And I'm not talking about I love using computers or I love gaming on computers. I think these wonderful machines running on electrons and magic smoke are a modern miracle, built on millions of hours of human endeavor, effort, and endurance. For my part, I've really enjoyed learning how these devices work, how they can turn electrons into integers, and integers ultimately into worlds, and then connect people around the globe to share those worlds. Some time ago, I built a JavaScript version of the Little Man computer, and that was a fun project. These paper computers taught a generation how to use a computer in an era before market forces made it possible for everyone to have access to one. It's a very fun project, but paper computers are more limited in terms of how a computer actually works. So now it's time to take this to the next level and let's start a new project. I've decided to build the SAP, or Simplest Possible Computer, from the book Digital Computer Electronics by Malvino and Brown.
I don't want to get any major online retailers in trouble, but I didn't buy this book in India. Also, it's a very recent book because the keyboard they show here, it's the same keyboard I have.
Call this computer primitive is an understatement, but hey, it's more powerful than a sheet of paper. And the thing is literally called the simplest possible computer, so really we're buying exactly what's being sold. But here it is in all its glory, an 8-bit bus, 16 bytes of RAM, and 8 LEDs for output. What more could you ask for? Plenty, but I digress. Now, the astute amongst you might recognize this as the same machine Ben Eater builds in his series of building a computer on a breadboard, which that's great, and if you haven't seen Ben's video, then I highly recommend you check out his channel. However, for this, I'm going to follow the inspiration for the Little Man computer, and we're going to build this machine as a software project. Now, some of you might be asking, why build a computer in code? And that's a perfectly valid question. So, let's take a look at the computer Ben built in all its marvelous blinky glory. Now, hypothetically, let's suppose one of these wires is loose. Breadboards are notorious for flaky connections, and even one loose wire might be enough to stop the entire system from functioning. Is that what I want to deal with? Well, no. What I want is I want to be able to fire this computer up, write some programs on it, have some fun. What I don't want is to turn the thing on and spend the next hour troubleshooting the latest issue that's going to pop up. Same reason I don't use Arch, by the way. Another thing to consider is the size of this thing. I'm not exactly, how would you say, blessed with the kind of abundance of space that I can leave this thing set up forever. And moving it around, well, remember what we were saying about connections being flakier than a nice fresh croissant? And finally, breadboards, chips, wires. These things cost money, but code is nice and cheap, and frugality is a virtue. Oh, and hand wavy open source virtue signaling. Anyone can download and use this for themselves, inspired the next generation, blah, blah, blah. Code is cheap. So, what are we going to be using? Well, the little man was built in JavaScript, not a framework, not a node project, vanilla JavaScript, like the good Lord intended. But this time, I don't want to make this for the browser. One of those little nagging thoughts that keeps rattling around in my head is that when you build something for the browser, it should probably support mobile. But the little man just wouldn't work for that. Phones and paper are just different aspect ratios, and scaling it for the mobile screens introduces readability issues, and splitting it into multiple sections makes it harder to see all the parts working together, and we're adding a lot of extra work to make this thing work on a format it was never intended for, and yeah, I'm just not going to go there again, worrying about things that the end user's never even going to consider. So this time, let's make it in Python, as a GUI application, using PyQt6. Why Python? Well, it's a popular language. I've enjoyed making projects on the Raspberry Pi with it, or other applications, and it's one of those languages where it's really easy to get into the flow state. So I'm using Python. Why use Qt or Qt or whatever the hell they want to call it for the GUI? Well, tkinter has always been my go-to in the past for GUI applications, but tkinter it's definitely starting to show its age. So let's get some more practice in with Qt. And with that decided, let's talk exactly about what it is we're building. So here we have the block diagram for our system. Now, in an electronics build, each of these boxes will be built up using a series of chips to accomplish the function of each block. Thankfully, since we're building this in software, we don't really need to create a one-to-one relationship for each of the chips in the system, and we can sort of consider these things in a more abstract sense. Now, what probably jumps out to most people first is the large bus bar at the center of the diagram. and that nearly every box has zeros leading to or coming from the bus. The bus is a common connection and allows us to transfer information from one section of the system to another. And by controlling what sections are writing to or reading from the bus, we can build up a series of micro instructions allowing us to effectively coordinate these parts and execute our program. The next thing you might notice that many of the blocks have a clock line leading into them, and that each of those has a funny little black triangle on the inside of the box. What that denotes is that this line is edge triggered, meaning that it's only going to be active during a very brief moment when the line first goes high. But before we get ahead of ourselves, where's our clock signal coming from and what are the other lines? This is where we need to talk about one of the few sections not connected to the bus, the controller sequencer, from which we're going to see 12 signals coming out. But where did they go? Well, if we take a look at the rest of the system, we'll see that between the various sections, there are 12 different lines that seemingly come from nowhere. These are our control signals, and that's what we're going to use to determine what writes to the bus, what reads from the bus, and when chips are going to take their own unique actions. Naturally, we could have connected these signals on our diagram, but that would get messy in a hurry, hence our lines going into and out of the ether. We can also see that roughly half our signals start with an L, and the other half start with an E. If we wanted a section writing onto the bus, we would fire the E for export or enable, which is going to cause it to output its data onto the bus. For the chip we want reading that data, we'd enable the L for load or latch. In an electronic system, we'd want to give the chip some time to settle out. The exact amount of time is something we'd find in the chip's data sheet. This is why the clock line is edge triggered, so we can ensure that all the sections are set up properly and then raise the clock line to capture the state at that moment. So we have our control signals that control the various portions of the computer and let us execute a program. But how does the computer know where it is in that program? Well, this is where the program counter comes in. Well, let's consider that we have our program mapped out in memory. Well, if the memory is a map of the instructions and data that make up the program, then the program counter is going to be that little star that says you are here. With this, we can get to our first instruction in what's called the fetch cycle. If we have the program counter export onto the bus and the memory address register latches that data, we've completed the first step. The memory address register is directly connected to the RAM. These 4 bits control which memory location in the RAM is going to access, and that sets us up for the second step in the fetch cycle. So let's write out the contents of the RAM onto the bus and load that into the instruction register. While we're at it, we can also increase our program counter by 1 to set up the next instruction. Congratulations, we've just completed the fetch cycle and we're ready for the execution phase. Now, our value loaded into the instruction register is directly fed into the controller sequencer. How does the computer make sense of this? Well, let's say we want our program to take a data value at address 15 and put it into the A register. We can take our 8 bits of RAM. The first 4 bits will give you a unique combination that means load memory into the A register. What combination of bits will do that is entirely up to us. So for our purposes, let's say 001 means load A. And what do we want to load into the A register? Well, the data address 15. So let's set the last 4 bits to be 15 or 1111 in binary. For the first step of the execution cycle, we'll set the memory address register to 15 by exporting from the instruction register and latching into the memory address register. For the second step, let's take our new RAM address and put what's stored in address 15 onto the bus. We'll have the A register load that value. With that done, we're ready to move on to a new instruction by beginning a new fetch cycle. The value of the program counter is now put into the memory address register, and the cycles will continue step by small step until the computer has completed its task. That's probably a lot to take in all at once, but with the basic theory under our belt, we can begin the next phase in designing our simplest possible computer. Until next time, thanks for watching. Cheers and cheerio.